Hey y'all, welcome back. Today we're going to continue our unit on limits, and specifically we're going to focus on a topic that we've looked at and kind of touched on for a few lessons now, and that is this idea of continuity. So today we're going to more explicitly define what it means for a function to be continuous, particularly at a specific point, and we'll be able to answer some questions that involve this idea of continuity. So let's first define it, and then we'll go through some examples of questions I might ask that involve continuity. Before today, I described continuity as saying if you had a function that you could draw without lifting your pencil, so meaning like no holes, gaps, vertical asymptotes, jumps, or anything like that. If you could draw the function without lifting your pencil, then the function was considered continuous. But one thing I didn't really get too deep into was like, what do we mean by continuity at a specific point? Like, can a function be continuous just at a single value? And it can be, but it has to satisfy this condition where the limit as x approaches that c value must be equal to the value of the function at that point. So in other words, like if I had a hole, I would not fit this definition. So like let's say I had a graph that did something like this. You know, it's going in either direction. You know, if I tried to draw this without lifting my pencil, I would have a hard time because I'd have a little hole here that I'd have to jump over and then continue on. So we can see real quick by my earlier sort of rough definition that this function is not continuous as a whole, but it is continuous at many places. So like it's continuous basically everywhere except for where this hole is. And that's because the continuity is broken right here. We no longer satisfy this statement. So let me explain exactly what I'm talking about here. So first of all, a function f of x is continuous at a point c if and only if, just a little sidebar here, that is not a typo. That means if and only if. And I'm not going to get into a lot of detail on why that is, but basically we have a biconditional statement versus a conditional statement, meaning that if this is true, then this is true, and also the opposite is also true. If this is true, then this is true. So it's just a little stronger statement, the if and only if, and this is a pretty common way to shorten that up in mathematics. So that's what this means. So anyway, the point here is that what we need in order to have continuity at a specific point, so like the reason why the function is not continuous here is because the limit does not equal the value of the function. So like let's say that here's my x and y axes, and the y value here was like 5, and we'll say the x value was 6 or something like that. I'm just making these numbers up. But we would say that the limit as x approaches 6 is 5, right? We can see as we travel from the left and from the right that we're getting closer and closer to y equals 5. However, the function is not defined there. So while the limit, like this value would be 5, this value is undefined, right? If I try to plug in 6 into my function, there's no point there, so it'd just be undefined. And the fact that these are not the same means that the function is not continuous there. So when we test for continuity, you know, this says that there's 3 requirements, but there's really just one. I mean, these are just sort of like, these have got to be true in order for this to be true anyway. So, you know, the function has to be defined there. So if it's not defined at all, then, you know, it's not continuous no matter what. The limit has to exist. So the left and right hand limits have to be equal. And we talked about limits in our last lesson. You can kind of go back to see, you know, when does it exist, when does it not exist. And then finally, they have to be the same thing. So if we just sort of assume that it's defined and it exists, you know, unless we have some other information, then we can say that if these are the same, then we know that they're continuous. Now, if one of these doesn't exist, we can't really test their equality anyway. Like if one of these is undefined, like for instance, if we don't even meet this requirement, we can't even test this last one. So if we establish that both the limit and the value of the function have a value, then we can go ahead and test this last one. So we can be continuous at points other than just like this. We're just talking about a single point here, right? Where this is called a point of discontinuity. But all these other points in the function give us places where the function is continuous. Like let's say this was at 3 and this was at 2. Okay, so again, just kind of making up numbers here, but the value of the function when x is 2 is 3. So we say like f of 2 is 3. And then if we look at the limit as x approaches 2, I'm going to have to use a different color here. So if we go from the left, if we approach x equals 2 from the left, approach x equals 2 from the right, we see that both of these are sort of converging on this value of 3. And so we would say that the limit as x approaches 2 of this function f of x is also 3. So since these two things are the same, we say that the function is continuous here. So a lot of times what I'm going to ask is, hey, where are the points of discontinuity? Like, where is the function discontinuous? But also tell me, where is it continuous? What are the intervals for where we have continuity? And in this case, we would have two intervals of continuity. We would say it's continuous from negative infinity to 6, but also continuous from 6 to infinity. Okay, so these are the places where we have continuity, so it's continuous on these intervals. And then we have a discontinuity at x equals 6, obviously. So that's pretty much the gist of it. So let's go into a little bit more detail, look at some examples, and hopefully by the end of this, you'll have a better understanding of continuity. So we've seen lots of different functions this year, particularly when we looked at piecewise functions that had these points of discontinuity. Now, there are different ways that a function can be continuous. For instance, you could have like a hole, like in that example I gave previously, or you could have something like a vertical asymptote, which is also a point of discontinuity. So we want to classify these points of discontinuity as either removable or non-removable. So a removable point of discontinuity is one in which you are only basically missing one point. So if you can just either add or move a single point, and that would cause the function to be continuous at that point, it is considered a removable discontinuity. So if you can, or if the function can be continuous at the point of discontinuity, let's fix that spelling there. Yikes. Okay, if the function can be continuous at the point of discontinuity by moving or adding a single point, then that point is a removable discontinuity. Okay, and this more or less happens when your limit exists, but the function is not defined as the same value. So if we go back to the definition of continuity, if it's discontinuous because the limit does not equal the value of the function, then that's when we have a removable discontinuity. And really, you're going to get one of two cases here. Either you're going to have just like a hole in the graph. Okay, so we call this a hole discontinuity. That's a specific type of removable discontinuity. Or you might have something else kind of similar where you have a hole, but the function's defined elsewhere. So let's say it's just defined like a little bit below it. So in either one of these cases, these are both kind of considered hole discontinuities. But in either of these cases, we can, like in this top one, we could just like add a point right here, and if I just included that point in the right spot, it would be continuous. Here, if I were to just like move this point up, this would also be continuous. So as long as it just takes like a single point difference from being continuous or not, then that's called a removable discontinuity. A non-removable discontinuity is when you'd have to move more than one point to make it continuous. So let's see, if a function can be continuous at a point of discontinuity by moving or adding more than a single point, then it is a non-removable discontinuity. So examples of this would be like a jump function. And so we'll talk a little bit more about jump functions. But basically that's when you have like one section. We see this a lot with piecewise functions. So we've got like one piece of the graph, and then the other piece of the graph is just kind of disconnected like this. So I could like move this whole section right here, right? And move this up, but that's moving more than one point. Okay, so if I have to move more than one point to make this continuous here, like if I just move this point up here, I'm still got a discontinuity because the left-hand limit's not going to equal the right-hand limit. So anytime you got to move more than one point, that is called a non-removable discontinuity. This particular type of a non-removable discontinuity is called a jump. Okay, and then if you another kind of non-removable discontinuity is when you have something like a vertical asymptote. So let's say we had like the function 1 over x, right, which kind of looks like this, and it has some asymptotes here, like a vertical asymptote, horizontal asymptote, but this would be an example of what we call an infinite discontinuity. Okay, this is an infinite discontinuity. And so basically what's going on here is the function, the limit does not exist. Like let's say we want to see what's going on as x approaches 0. The limit doesn't exist there due to that unbounded behavior. And when you have a limit not existing due to unbounded behavior, you say that it's an infinite non-removable discontinuity. So we've got like 4 examples here, and I think the easiest thing is just kind of identify them by their shape when you see them on the graph. But it is nice to be able to classify these as being either a whole, a jump, or an infinite discontinuity. All right, so let's take a look at an actual function here and see if we can find any points of discontinuity. So when we look at a rational function in particular, there are 2 different things that would cause a discontinuity. So way back when we talked about rational functions, we saw that there was 2 things that could make this kind of function undefined. Okay, we're looking for holes, and we're looking for vertical asymptotes. So anytime we have an x value that we have a hole at, that's going to be a point of discontinuity, and we're going to classify it as a removable discontinuity. And anytime we have a vertical asymptote, like this one, then that is going to be a non-removable discontinuity. So we're going to find and classify the points of discontinuity, and then state the domain of the function. And the domain is just going to be, for this type of function, it's going to be everywhere where the function is continuous. So everywhere where we don't have either a hole or a vertical asymptote. So to be able to find the holes or vertical asymptotes, let's just quickly review this. What we have to do is we've got to factor that denominator. So I'm going to rewrite this function, and it is f of x equals, we got a little fraction going. Oh, let's get it. There we go. So we got x plus 1 on top, and on the bottom this is a pretty simple factoring. It's just going to be x plus 2 times x plus 3. If you have any questions about factoring, just reach out to me. Oh, not x plus 3, what am I doing? X plus 1. If you have any questions about factoring, just reach out to me, and I can kind of guide you through that, or just check out one of my old videos. You can go back to my Algebra 1 videos where I go over step by step how you factor. But anyway, once you get it factored, you can see that we've got a common factor here. So just a little refresher here. Any value that makes the denominator 0 is going to make this whole thing undefined. Okay, so that's going to happen in 1 of 2 ways. One is either like if you don't have another factor up here, then it's going to cause a vertical asymptote. So like in this case, we've got a vertical asymptote at -2. Because if this was -2, that would make this 0 and then causes no other issues. Well, I mean, besides the fact that it's undefined. Now, you notice you've got x minus 1 in both the top and the bottom. So that means that we're going to have a hole at x equals -1. So just as a little reminder, holes occur when x makes both the numerator and denominator equal 0. In other words, you have the same factor on top and bottom. Okay, So that's where we get the wholes, and then we get vertical asymptotes when x makes only the denominator 0. Okay, so what we want to look at here is the two values that are going to make the denominator 0, and then just kind of ask ourselves, well, is that going to be a whole or vertical asymptote? So I've kind of already answered that here. X equals -2 is a whole, so that is going to be a point of discontinuity. Okay, so x equals -2. Let's classify that. We have a whole there. I'm sorry, not a whole, but a vertical asymptote. So that is a non-removable discontinuity. And if we want to be more explicit about it, we can say it's an infinite discontinuity, right? Because that's where we have a vertical asymptote. And then we also are going to have a point of discontinuity at x equals -1, because that would also make the denominator 0, but that also makes the numerator 0 too. So anytime you've got an x value that makes both the numerator and the denominator 0, like when you have the same factor, that is going to be a whole. So we'll have something like this. This is a removable discontinuity. So I'm going to edit this and say, okay, well, x equals -1 is a removable discontinuity, and to classify it even further, we say it's a whole discontinuity. So, I might ask you to classify it either way, just kind of simply, is it removable or non-removable? But I might also ask, hey, go one step further and tell me, is it a whole, is it a jump, is it, and why is it discontinuous? All right, so the last part of this is to give the domain of the function, which is going to be all real numbers except for these points of discontinuity. So the domain here is going to be all x values. Let's see if do I have that particular symbol? I might just have to draw it in here. So I'm just going to leave a little space here for that is an element of, and I'll just hand draw that in. And then so it's going to be from -infinity to -2, and then we should have like a big U symbol, okay, and then from -2 to -1, and then from -1 to infinity. So basically saying all real numbers except for -2 and -1. So that this is how you would write it if you were using set notation. And here's my little set symbol, like x is an element of this set. It's kind of ugly, but that's basically what it should look like. Okay, so that's one way to write the domain. You can also write it as a inequality, and I don't really care which way you do it, but here's how you would write it as an inequality. You could say that x is less than -2, well, let's see, this is not going to be very friendly here, or x is in between -2 and -1, or you can kind of see, hopefully you kind of see why I prefer the set notation, or x is greater than -1. So a little bit more tedious in terms of writing the whole thing out. Just trying to clean this up a little bit. So you can write it either way. Quite honestly, I will tend towards the set notation way of writing it. Okay, like up here, I just think it's a lot easier to write because you're just kind of going from left to right. Whereas here, you got to be real careful about your inequality statements. Okay, so either one of these is fine. I like this one, but this is okay too. There's actually one other way you could write it, which might even be the best way here, and say that x is all real numbers except the places where it's undefined. So x does not equal -2 or -1. Okay, so that might be the most efficient way of writing it. Okay, so these are just like 3 different ways how you can write the domain. These first 2 are saying where the domain is, and this one's saying where the domain isn't. So sometimes it's easier to describe something by saying what it's not. So I'm kind of going way more in detail on the domain here than you really need. But basically, you want to just include all real numbers except for these points of discontinuity when you're dealing with a rational function. So here's another function that we haven't really talked about much, but we'll see a lot, especially within the context of continuity and limits and all that good stuff. And this is called the jump function. So this is kind of an interesting function where, okay, so let's just say we have the absolute value of something divided by itself. So before I even get into this more generic version of the jump function, just imagine you have something like the absolute value of x over x. Okay, so absolute value of x over x. And what does this equal? Well, if x is positive, then this is just going to equal whatever the number is, right? So like if x was 5, the absolute value of 5 over 5 is 1, right? So if the x is 10, the absolute value of 10 is 10. 10 divided by 10 is 1. So as long as this number is positive, then our function will equal 1. Okay? Now, it can't equal 0 because it can't divide by 0, so we're going to do a little open circle. But what about if it's negative? So if x is negative, like let's say we have the absolute value of negative 3 over negative 3. Well, the absolute value is going to turn this negative 3 into positive 3, and so you'd have 3 over negative 3, which is negative 1, right? And that's going to be true for every single negative value here, is you would have negative 1 as your result. So it's called a jump function because you're kind of jumping up from negative 1 to 1. So we can sort of generalize this idea of beyond just x over x, and we can add or subtract some constant here. So let's say we have x minus k, the absolute value of x minus k over x minus k. Now, as we know from our discussions on transformations, if you add or subtract a number to your input, to any particular function, that's going to just shift it left or right. So if I have x minus k here, that means I'm going to shift to the right k units. So whatever k is, that's going to be where this jump takes place. So like if I have something like x minus 3 over x minus 3, this is always going to equal 1, except this is always going to equal positive 1 if x value is at least 3. Or, I'm sorry, more than 3. So if I go back and erase this real quick, we don't really need this anymore. Okay, I guess you don't need to wait for all this. We're going to draw this function at, say, okay, well, at 3, we've got a function go to the right, right? Because it's always going to equal 1. Like if I plug in 10 here, then I get the absolute value of 7 over 7, which is 1. If I plug in 100, I get 97 over 97, which is 1. No matter what, if it's bigger than 3, it's going to equal 1. Now if it's less than 3, it's going to equal negative 1. So we're always going to have a point of discontinuity here at whatever this k value is. That's where the jump happens, and that's going to be a non-removable discontinuity like this. So in general, let me go ahead and sketch this out for you, and I'll erase everything I have here. If the value is k instead of like 3 or something like that, then you're going to put this wherever k is, and if k is negative, like if this was actually x plus 3, then it would go over here, right? But since the way this is set up, we're going to go to the right. So whatever that value of k is, to the right of that, we're going to be equaling 1, and to the left of it, will equal negative 1. So this is sort of your generic function. These should be horizontal. Might not look like that because I'm freehanding it, but this will be 1 and this will be negative 1. So that's the basic graph. So once you understand what the graph is going to look like, now it becomes a little easier to find the points of discontinuity. So for example, this one down here, I'm just going to do a quick sketch of the graph. And this is going to be pretty rough, okay? So we're just trying to get the idea down here. Don't worry too much about, oh, it's like perfectly accurate or anything. So we're going to put 5 right here. We're going to label this as 1. We're going to label this as negative 1. And so we know we've got an open circle here going to the right and an open circle down here going to the left. and that is supposed to be a horizontal line. But anyway, okay, so find any points of discontinuity. Well, we obviously have this one at 5, and this is a non-removable discontinuity because I can't just move one point and make it whole, right? I could do that with the whole. So that's why that whole was the removable discontinuity up here. This is a non-removable discontinuity. So I'm going to label it as such. So I'm just going to make a little note here. Actually, I'm going to copy this just so I don't have to retype everything. It's not an infinite, but I'll change that here. All right, so what we have here is we have a non-removable discontinuity, right? Because I have to move more than one point to make it continuous. And it's going to be at x equals 5. And it's not an infinite discontinuity like that last one. This is what we call a jump discontinuity. Kind of fits the whole, we're calling it a jump function. That's like your huge clue here. But really, you just want to be able to recognize this kind of a function so you know right away what it looks like. You've got a lot of experience with like y equals x squared. You probably have a mental picture right away of what y equals x squared looks like. You want to have a good mental picture of what this one looks like too. So there'll be, one or a couple problems on your homework and whatnot where you have to analyze a jump function. So anyway, that's our discontinuity. The domain is going to be all real numbers except for whatever this k value is. In this case, it's 5. So we can just say that the domain is just simply x is not 5. That's probably the easiest way to write it. I showed you on the previous example how you might write this otherwise, either using the set notation or just going all out with the inequalities. But sometimes it's just easier to describe the domain by saying what it isn't. Okay, if you're saying it's everything except for 5, that's equivalent to saying x is not 5. So here's our classification of the discontinuity and the domain. Now, let's change gears just a little bit here. And this is a kind of problem that we've worked out before, but now we're just going to make it just a tad more complicated here. So this is where we want to find values that make the piecewise function continuous. Now, like I said, when we talked about piecewise functions, I showed you how to work this kind of a problem. But I just want to show you something that might get a little bit more complicated here. Might involve some logarithms, or I've got one other problem here that I want to show you where you've got multiple variables. But let's say we want to find a value of k that would make this continuous at x equals 1. So what's really going on here is you've got like this linear function, you've got this other kind of combination of a linear and a logarithmic function. And these are two separate pieces that will most likely be disconnected, and our goal here is to figure out, okay, what number do I need to plug in here and here to make them connected? So let me bring up Desmos real quick just so you can kind of see what's going on here. And notice here, let's make this real big. So I've got this set up. Well, if you can see it, there we go. So I've got this set up with the two equations, the 2x minus k for when x is less than 1, and the natural log of x plus 4k for when x is greater than or equal to 1. And you can see that they're disconnected just if k is 1. And as we change the value of k, we can kind of shift these around. And what we're looking for is the value that's going to make them connected so that the thing can be continuous, right? We want the value of the function to equal the limit. Now, it looks like we're getting pretty close here. It looks like it's about 0.4. If I zoom in here, it looks like 0.4 might be our winner. Maybe it's 0.41. I mean, it's not 100% obvious, but if we get something that's 0.4 or around 0.4, we should be pretty confident that we got the right answer here. So, this is kind of the idea of what we are trying to do. So let's see how that works out algebraically. Though what we want these two functions to equal each other when x is 1, right? We want the value of the function to be the same for both of these. So that way we know it's continuous. So I'm going to set up an equation here, 2x minus k. We want both of these to be equal. But specifically, we want them to be equal when x is 1. Okay, that is the point of discontinuity that would exist unless they're connected. So we want to ensure that at x equals 1, we get the same value for both functions. So that way we know they're right next to each other. So what I'm going to do is I'm going to plug in 1 for x, everywhere I see x, so 2 times 1, natural log of 1, and then we're going to solve this for k. Now, luckily, 1 is kind of a convenient number, especially because we're dealing with logarithms here. The natural log of 1, and actually the log base anything of 1, is going to be 0 because anything to the 0th power is 1. So we've got 2 minus k equals 0 plus 4k. Now I'm going to rearrange some things here. I'm going to add the k to make this 5k, and then so what I get here is 5k equals 2. Just kind of move some things around there to clean this up. And then if I divide both sides by 5, I do get k equals 2/5, which is 0.4, right? That is the value that we saw in Desmos, which is kind of cool. That, you know, if you're working out algebraically and what you get algebraically is what you see in Desmos, then you are in pretty good shape. Okay, so 0.4 matches up with what we thought it was going to be. So there we go. That's how you find k. Now, like I said, we've worked out problems like that before, so this is not, should not be something new. But just don't be scared by the logarithms. Usually they're going to be set up so that these work out pretty nicely. Now, one last problem here is going to be very similar, but check this out. Here we've got two values we need to kind of make work so that these three pieces match up. So we've got to make this first piece match here when x is -1, and then we needed to make the second piece match the third piece when x is 3. So there's going to be basically 2 points of discontinuity at -1 and 3, unless we make these a and b values sort of work so that won't happen. Let's take a look at what that might look like in Desmos. So here we are, and we can see the three different pieces here. The first one is for when x is less than or equal to -1. The second one's in between -1 and 1, and then the third one, that's 2x, is everything greater than 3. I'm sorry, not between -1 and 1, -1 and 3. So what we want to do is we want to find some combination of a and b here that'll kind of make it match up. So if I change a, I can kind of get that one to match up, right? But then the second and third piece aren't equal. So I also need to change b somehow to make that kind of work for me. So if I can kind of play with these to kind of, get close here. You can see I'm kind of getting close, but this could take a while, especially, oh, look at that. Ooh, I think I might have found it. I didn't even really mean to find it right like that. But, okay, so here's the thing. I think it's at 1 and 3 just by looking, kind of playing with the numbers here. But it could be something like 1.1 and 2.9. So we need to be able to solve this algebraically to know exactly what the a and b values are. But if there's something around 1 and 3, then we're probably in good shape. So let's go ahead and work it algebraically here, see what happens. So we've basically got to satisfy two different equations here. We've got to make sure that the first segment equals the second segment, but we also need to make sure that the second segment equals the third segment. Oops. So we got to satisfy both of these equations simultaneously. Now, for this first piece matching the second piece, we need that to occur when x is -1. Right, that's where the first piece meets the second piece. And then the second piece meets the third piece at 3. So back here, when we plugged in this x equals 1, we only had to worry about one thing because we only have one equation, but here we got two equations. So we're going to plug in -1 into the first equation, and then we're going to plug in 3 into the second equation, wherever we see x. So here, we've got -2 times -1 equals a times -1 plus b. And for the second equation, we've got a times 3 plus b equals 2 times 3. So I'm gonna clean these equations up a little bit. You can hopefully see, for better or for worse, what's going to end up happening here is we're going to end up with a system of equations that we're going to have to solve. But luckily, it shouldn't be too bad in terms of the complexity. So let's go ahead, and I'm just going to copy this over, and we're going to move things around, okay, and kind of simplify this. So -2 times -1 is just +2. -1 times a is just going to be -a. And then for the second equation, we got a times 3, which is just 3a, and then 3 times 2 is 6, So we're looking like we've got a pretty nice couple set of equations here. I'm actually going to move this one around just a little bit so that it looks more like this, and we can use elimination as our method of solving. You can use substitution here, but I think this one is going to be easier with elimination. So like if I add a to both sides and subtract b, I'm going to get a minus b, and then I want to move the 2 over, we'll get negative 2 on the other side. So just kind of moving that around. All right, so there we go. Now we've got two equations with two variables here. We need to solve this as a system of equations because both of these have got to be satisfied. So elimination here is going to be the method I'm going to use, okay? But you may know another elimination. You may know another method like substitution that will also work, but I'm just going to go with the elimination method. Whoa, what's going on there? There we go. Okay, so the elimination method is when you combine the two equations in such a way that you get one of the variables to cancel out. So what I'm going to do is I'm just going to add these two equations together, like in columns here. A plus 3a is going to be 4a. Negative b plus b is going to be 0. That's what I want to happen. I want one of the variables to be eliminated. That's where this method gets its name from. Negative 2 plus 6 is 4. And then if I divide 4 by 4 on both sides, I get a equals 1. Now I believe that that is what we got on our Desmos thing. We'll double check that when at the end. But we got a equals 1. So now we need b. To get b, we need to plug that back into either of the equations. Doesn't really matter which one. I'm going to pick this one, just sort of arbitrarily. But you could plug it into this one. Doesn't really make a difference. And so we get 3 times 1 plus b equals 6. 3 times 1 is 3. Don't need a calculator for that. And then if I subtract 3 from both sides, I get b equals 3. So I get a equals 1 and b equals 3. Those are the solutions I got, and I'm pretty much done here. But let's go back to Desmos just momentarily. See if that's what we got. Okay, that is what we got, the 1 and the 3. So a was 1, b is 3. We can see that visually, that we have made this function, this piecewise function, continuous. So we're in good shape. We got it. So that's pretty much it for today. Hopefully at this point you have a better understanding of what continuity means and how to identify if a function is continuous and be able to classify these points of discontinuity as either being removable or non-removable, identifying them as a jump or an infinite or a whole discontinuity, and also be able to solve some equations where you have to make a piecewise function continuous. Y'all have a great day, and I'll see y'all next time.